It only took 3 pieces of evidence together to completely revolutionize our picture of the universe in the early 20th century. We had previously assumed that the universe was static and unchanging, and that the entirety of existence was contained within the Milky Way. The spiral and elliptical nebulae in the sky were assumed to be objects, perhaps newly forming protostars, within our own galaxy. But then, by the late 1920s, everything changed. The combined facts of Einstein's general relativity superseding Newton's universal gravitation as our theory of gravity, individual stars being observed in those spiral and elliptical nebulae, allowing us to confirm their extragalactic nature and to compute the distance to them, and the observational shifting of atomic lines towards either redder or bluer wavelengths from spiral and elliptical galaxies overturned that picture entirely. The universe, on the largest of cosmic scales, wasn't static and unchanging at all, but rather was dynamically expanding. If that's true, and the universe is expanding, then what else is expanding along with it? Is our galaxy expanding? What about the solar system, planet Earth, or even the atoms in our own body? When Einstein first put forth his general theory of relativity in late 1915, it reimagined gravity not as an invisible, instantaneous force between 2 physically separated massive objects, what Newton called action at a distance, but rather as a consequence of the curvature of the very fabric of spacetime itself. Mass and energy, according to Einstein, would cause the fabric of spacetime to curve, bend, distort, and even evolve in a particular fashion, and then whatever structure that spacetime takes on determines how the matter and energy present within it moves and evolves. To paraphrase John Wheeler, matter tells spacetime how to curve, and then that curved spacetime tells matter how to move. Because Einstein's field equations are extremely general, and are capable of describing any spacetime that could conceivably exist, even if only in our imaginations. It's up to us to extract what are known as solutions to those equations. The simplest exact solution is for completely empty, flat, non-evolving spacetime, the Minkowski spacetime of special relativity. The next simplest solution, also derived by Einstein, was for the weak field limit, being far away from a single-point mass, the almost Newtonian-like spacetime of a mass at a distance. But over the next few months and later years, a number of important and exotic solutions were found. In 1916, Carl Schwarzschild wrote down the spacetime solution for a point mass without being restricted to weak field assumptions, now equated with the case of a non-rotating black hole. In 1917, Willem de Sitter wrote down the spacetime solution for a universe filled with a cosmological constant, what we now call de Sitter space, and which describes both cosmic inflation and dark energy. And in 1922, Alexander Friedmann wrote down the spacetime solution for a universe filled, uniformly, with any species, or even multiple species, of matter and/or energy. In the case of a black hole, or any other spacetime that's dominated by a bound structure, the spacetime doesn't expand and objects within it don't recede from one another. However, in the latter 2 cases, it turns out that the spacetime for a universe that's filled uniformly with stuff, whether a cosmological constant, matter, radiation, or any other species of energy, cannot be static and stable, but must evolve either expanding or contracting over time. In the 1910s, astronomer Vesto Slipher used the technique of spectroscopy to break the light from astronomical sources into its component wavelengths. As you'd expect, whenever you perform spectroscopy in a lab or on our own sun, you'd find that atoms of a particular species, hydrogen, helium, calcium, potassium, always both emitted and absorbed light at the same set of wavelengths that corresponded to the quantum transition of electrons within that atom. When you instead performed spectroscopy on one of those spiral or elliptical nebulae, however, you'd see something different. All of those same spectral lines still exist, but they're all shifted by a multiplicative factor towards either longer wavelengths, if the factor is greater than 1, or shorter wavelengths, if the factor is less than 1. Shifts to longer wavelengths are known as redshifts, because red colors are at longer wavelengths, whereas shifts to shorter wavelengths are known as blueshifts, as blue colors are at shorter wavelengths. Now here was the kicker to Slipher's observations. The nebulae that look larger and brighter in the sky, presumably because they're closer, were a mix of redshifted and blueshifted, and only by small amounts. But the nebulae that look smaller and fainter were all redshifted, and by much greater amounts. Our next clue in the cosmic puzzle came in 1923, when Edwin Hubble made a groundbreaking discovery that would forever change our understanding of the universe. Hubble observed faint flares in the Great Nebula in Andromeda, initially misidentified as novae. Upon closer examination, these flares appeared to repeat, revealing their true nature as variable stars. Thanks to the pioneering work of Henrietta Leavitt, who established the relationship between a variable star's periodicity and its intrinsic brightness, Hubble could measure the distance to these stars. This technique confirmed that the Great Nebula in Andromeda was not within our Milky Way, but was, in fact, the Andromeda Galaxy. This revelation was monumental. It meant that the universe was far larger than previously imagined, with galaxies existing well beyond our own Milky Way. But Hubble didn't stop there. Along with his assistant, Milton Humason, he measured the distances to various nebulae, expanding our cosmic map. Around the same time, Belgian scientist Georges Lemaitre concluded that the universe was expanding. Today we have measured the redshifts and distances to hundreds of thousands of objects in the nearby, intermediate, and ultra-distant universe, from modern times all the way back to just a few 100 million years after the Big Bang. Not only have we confirmed that the universe is expanding, but we've used the power of Friedmann's original 1922 equations to determine the ratios of the various species of energy that permeate all of the universe. We've learned that the universe today is made of 68% dark energy, behaving as the cosmological constant examined by de Sitter, 27% dark matter, which acts like a form of mass but doesn't experience any interaction other than gravity, 4.9% normal matter, which includes protons, neutrons, electrons, and everything they come to form, 0.1% neutrinos, which behave as radiation when the universe is hot and young, but then behave as matter when the universe is cold and old, and 0.01% photons, which always behave as radiation. On cosmic scales, the Friedmann equations tell us what the relationship is between the evolution of space, and specifically, the evolution of the distance between any 2 points in space, and the matter and energy contents of the universe at any moment in time. If you can measure the expansion rate today and how it's evolved over time, you can determine what's in your universe right now, as well as what it was like in the past and how it will evolve into the future. With good enough observations, we can determine our ultimate fate. But not everything expands uniformly. There are plenty of galaxies that don't obey the equations for the expanding universe in any exact fashion. The closest example we have is the Virgo cluster, located some 55 to 60 million light-years away. Based on our measurements of the expanding universe and the distance to the Virgo cluster, we'd expect to find the galaxies within it receding from us at approximately 1,200 kilometers per second, give or take. But that's not what we measure when we make the critical observations. Inside the Virgo cluster are thousands of galaxies. Some of them are actually headed towards us, exhibiting a small but measurable blue shift. Most are headed away from us, yet around half of the galaxies we observe have too low of a speed, between about 0 and 1,000 kilometers per second. Additionally, about half of the galaxies within the Virgo cluster have a greater than predicted redshift of more than 1,200 kilometers per second, with some receding at even more than 2,000 kilometers per second. So why are these galaxies not obeying Hubble's law? And why are they in violation of the Friedmann equation's predictions? For the same reasons that planets orbit the Sun in the solar system and stars move around the Milky Way inside our galaxy, because they're all mutually bound together through the force of gravity. These gravitational forces imprint what astronomers call a peculiar velocity onto these objects, a speed ranging from hundreds to thousands of kilometers per second that gets superimposed on top of the Hubble flow. The big question we need to ask ourselves whenever we're considering what governs the behavior of space is the question of what is governing the shape, curvature, and evolution of spacetime on the scales we're considering. Even though we're part of the expanding universe, most of what we're familiar with is not itself expanding. Atoms, bound together by the electromagnetic force, do not expand. Human beings, also bound together by electromagnetism, do not expand with the expanding universe. Features on planet Earth, which is bound together by gravity, do not expand with the expanding universe. If the Earth physically expands, however, due to factors like thermal expansion or core activity, then those features would expand. The Earth-Sun distance, again determined by gravity, does not expand as the universe expands. As the Sun loses mass, however, the Earth-Moon system spirals outward. A different effect dominates here. The distance between stars within the Milky Way, which is gravitationally bound, doesn't expand as the universe expands. And the distance between the Milky Way and the other galaxies in the local group, which again is bound by gravity, doesn't expand as the universe expands. We realize that while we are part of an ever-expanding cosmos, the forces that bind us are intricate and finely tuned. Thank you for joining us on this journey through the cosmos. Until next time, keep looking up and stay curious.